this work was done in my group in Max Planck Institute in Mainz, which is just half an hour drive to the south from here. So my postdoc Zoltan Mich was the main driving force behind the project. The samples also came from within the house, from our synthetic department at the institute, and we also had nice collaboration with Expo in Barcelona. Can you hear me like that? So is it okay? Thanks. All right. So graphene. Everybody knows what graphene is. It's a single sheet of carbon atoms arranged in hex lattice. The carbons, they are sigma bonded in the plane, and then the pi bonds, they stick out, and the conduction goes along the hybridized pi bonds. And around the point of minimum energy, this is called the K point, the energy momentum dispersion looks like a cone. And that implies the massless behavior of the carriers. And so that means the carriers, they always move with the same constant group velocity, so they behave like photons, yet they have a charge. Absence of mass changes the mechanics of motion of the particle. That means massless carriers will not obey to the Newton's second law. That means that in the massless carriers, they will accelerate or decelerate immediately. So the acceleration and deceleration is instantaneous. That also means that since there's no inertia, the particle will not bind. So massless carriers, they not only can move fast according to the group velocity, they also will not fall into the traps. They also will not bind into the excitons and so on. So trapping and exciton formation is the main limitation for organic electronics, like we all know, and graphene is a perfectly organic material where trapping and excitons is not a limitation at all. Then, of course, graphene is very compact, only one layer thick. And it also has a field effect, so you can control the conductivity by changing the potential on graphene. So it all looks super perfect for ultra-high-speed electronics, and indeed people started making the transistors out of it. Of course, you cannot make a logic transistor that you need to close, because graphene has no band gap, so you cannot move the Fermi edge into the band gap. But you can make a high-frequency amplifier, the HEMT-type transistor. So you have the source, drain, and then you have the channel, in which you change the conductivity by controlling the gate. And graphene has this linear dispersion, which is different from parabolic dispersion in normal semiconductors. That means that here, by changing the Fermi edge by Fermi level by factor of 2, you will change the conductivity by factor of 4. Yeah? And this is an advantage over, for example, normal semiconductors with the square dispersion. There you will only change the conductivity by 2 to the power 3/2. So how this transistor works, it's always in the on state. So the Fermi level is always in the band, and then you just modulate the Fermi level, and that will change, will translate into amplification of the current. And they can work at pretty high frequencies, and indeed the people started building the high frequency transistors out of this. So this is the map of the current status of ultra-fast transistors taken from the review of Frank Schwitz from 2 years back. Horizontal axis here is the gate length, basically showing you how small the transistor is, so how fast you can modulate it, limited by the RC factor, and the vertical axis is the cutoff frequency, which is the figure of merit for how fast your transistor is. So the vertical axis here is gauged in gigahertz, and here top stands 1000 gigahertz, which is a terahertz. So this is where the industry wants to go by making the transistor smaller and smaller and smaller, yeah, moving down this axis. It seems like we can enter the terahertz operation regime. What is color-coded here is different material systems. The red symbols are classical semiconductors like indium phosphide and gallium arsenide, and they operate at several hundreds of gigahertz, very, very close to 1 terahertz. And the people who make those transistors that operate at about 1 terahertz, they publish them in IEEE journals or in APL. So those green symbols here, they represent the status quo for graphene transistors. This was taken from a review of 2 years back, and it's still the world record. So the graphene transistors do not operate higher than about 400 or 500 gigahertz. And this is not because of bad engineering, as I will try to explain you in the next slides. When we want to understand the physical picture of this limitation of the high speeds for graphene transistors, we need to acknowledge the fact that graphene MOSFET, high-speed MOSFET, is a strong field device. If you have the gate length on the order of 100 nanometers and source-to-drain voltage of about 1 volt, and you can go much lower because you need to be much higher than KT, then the field in the channel will be on the order of 100 kilovolt per centimeter. And then you want to modulate the currents by this strong field at the terahertz rate. So what we did in my group, we didn't make a transistor, first of all, because we cannot, but we decided to check the performance of pristine graphene, very high quality graphene, in transistor-like conditions. So what we did, we measured the current voltage response of graphene as a function of frequency. To basically to isolate the intrinsic response of the material from the possible effects of the circuit that could also limit the performance of transistors. So this is how the experiment looked like. This is this infamous Terahertz pulse. So just to remind you, the Terahertz pulses, they are light waves that we measure directly as light waves. So we can measure the electric field in this oscillating light wave as a function of time. So this is how we measure them. We can also control the peak field in those light waves in up to several hundreds of kilovolts per centimeter. And then we send those Terahertz pulses from the free space onto the sample of interest. In this case, it was graphene sitting on the substrate. Substrate was given in doping, so graphene was conductive. The sigma is the conductivity. So this is just the expression for Ohm's law. So this Terahertz field will drive the currents in graphene. And then the Terahertz pulse that was transmitted through graphene will lose some of its power, which we can also measure in time domain. You see this one is smaller. And this decrease in the transmission means that you have dissipated some energy due to the conduction. You can then analyze the data, and then you can extract all the information you want. So in this experiment, we had access to all interesting field regimes, from the weak field, which is the linear regime, to strong fields, which is typical for transistor, about 100 kilovolts per centimeter. And also, if you Fourier transform the Terahertz waveform, then this is the frequency spectrum. And within one spectrum, you have the frequencies of the present generation of transistors, about 400 gigahertz, and also the target frequency for the industry, and the frequencies exceeding 1 terahertz. So we can measure all of that in one go, just by measuring these transmitted waveforms. All right, so without long ado, this is the result. So the horizontal axis is the peak electric field, so how strong the field is on graphene. And the vertical axis is the conductivity expressed in quantum units, and the frequency is color-coded. So first of all, the conductivity always decreases with increase in the electric field strength. So the stronger current you want to drive, the less conductive the graphene will be. But what's most troublesome is that the conductivity drastically goes down with the frequency. So if at strong fields, so I remind you that about 100 kilovolts per centimeter is the typical transistor field. You can still drive currents at about 400 gigahertz. There's still some reasonable conductivity left there. At the frequency exceeding 1 terahertz, the conductivity is basically zero. So basically, by increasing the frequency, we make the graphene resistive. So graphene becomes resistive at strong fields and high frequencies. So this is the observation. And in the next slides, I will try to give you a very simple physical picture that allows you to understand all that, even numerically. Let's forget for a moment about all things nanoelectronics and transistors and graphene, and let's think about some very, very basic thermodynamics. Let's imagine we have a box with a bunch of electrons. Now this is an electron gas. Statistically large number of electrons, they all move the way they want. And the total energy of this electron gas in the box is the sum of the average kinetic energies of all those electrons, which simply make up the thermal energy of the electron gas, right? Q, heat, which is proportional to the electron temperature. And of course, the box is stationary, so the net momentum is zero. The box is not moving. The distribution of such an electron gas is described by well-known Fermi-Dirac functions, where mu here is the chemical potential, and the Fermi-Dirac function is spread by the temperature. Is brought by the temperature. Very trivial. Okay. So now let's take one more electron, which has some kinetic energy and momentum, and then shoot it into this box like this. So at the time zero, when this extra electron just entered the box, we can differentiate it from all other electrons. That's this guy, the yellow one. Yeah. So now it brought new energy, the kinetic energy, and also brought new momentum to the system. And as it entered the gas, it will start interacting with all other electrons via electron-electron interaction. And this is a process that's difficult to describe analytically. You need to do some numerical calculation about microscopic electron kinetics. Very difficult, especially for experimentalists like us. But if we wait long enough, we'll know what's going to happen. The electron gas will thermalize, the energy will equipartition, so the energy will again be shared by all electrons within the gas. You see now they all move a little faster, those arrows are a little longer than before. And this extra kinetic energy simply added to the electron heat. So the only thing that happened in the long run is that the temperature of this electron gas increased due to the new supplied energy, which was kinetic energy of this extra electron. Now it's just extra electron heat that we brought to the system. And of course, then the box will start moving because the momentum must be conserved, so the current will flow. Okay? So thermalization redistributes all this extra energy among the gas. And then you can describe it again by a Fermi-Dirac function at some high temperature. So this is exactly what happens to graphene in Terahertz fields. Again, this is this famous Dirac cone, the linear dispersion of graphene. So what happens, so this is the graphene is doped, this is the Fermi level, then you apply this electric field, and then you start depositing the energy into graphene by driving the currents by a conductivity mechanism. Real part of the conductivity is proportional to the power absorption. So this is how you deposit this extra energy to the Fermi sea of graphene. And initially it's those ultra-fast microscopic currents that keep this energy, but because of this linear dispersion, the electron-electron interaction is very efficient. Actually, the electron-electron scattering is automatic because the energy momentum in linear bands is always conserved. So any two electrons, they can do this without the presence of the third particle. So this is very efficient, also very fast, and that leads to very, very quick thermalization, equipartition of this extra energy among the whole electron population of graphene. And this happens faster than 30 femtoseconds. And now compare this to 1 picosecond cycle of the Terahertz wave. Yeah? So the Terahertz wave oscillates much, much, much slower than the thermalization occurred, than the energy is shared among the whole electron population. That allows us to transition from Terahertz electrodynamics that needs to be treated microscopically to Terahertz thermodynamics, which is a purely statistical approach and also very simple. The conductivity of thermalized electron gas in graphene can be described by such a solution of Boltzmann transport equation. So here you can see the Fermi function, rather its derivative. So if you can describe the gas by one Fermi function, it's thermalized. There are important parameters here. There's the density of states, momentum scattering time, which can be energy dependent. Yeah, and then the Fermi function, which is energy dependent, depends on also the chemical potential and the temperature. Okay. The important thing, this is next slide will be the qualitative explanation of why graphene becomes resistive when you increase the electron temperature. Is that for the hot electron gas, the chemical potential must decrease in graphene. Yeah, so just bear with me for the next couple of slides, and then you'll understand why. The population density function, as you know, is a product of the Fermi function, which is a step-like function, and then the density of states of the material. So if you multiply these two functions, the step-like Fermi function with density of states, which in graphene is linearly increasing with energy, then you will have such a triangular function, which is the population density. Okay? So now let's increase the temperature of electron gas without changing the Fermi level, without changing the chemical potential. So now we made graphene hotter, electrons in graphene hotter. The Fermi function spreads symmetrically around the same chemical potential like this. And that will lead to such a population density function. Right? So just now you multiply this hot Fermi distribution with the same density of states. This is what you get. The total number of carriers in the material is the integral of the population density function. It's the area under those curves. And it must be conserved at all times. By making graphene electrons hotter, we will not multiply the number. So this quantity must be always conserved. And now even graphically, you can see that the area under the red curve is bigger than the area under the blue curve. Yeah? Because the integral of this curve is the integral of the Fermi function, which spreads symmetrically across around the chemical potential, which is integrated by the weight of the linearly increasing density of states. So this gain of the population at high energies is larger than the loss of the population's low energies, because density of states increases. Okay? And this is bad because this is the violation of particle number conservation. So if you make electron gas hotter by keeping the Fermi level of chemical potential constant, you will run into the violation of particle number conservation. The only way to conserve the particle number is to downshift the Fermi level. Yeah? So now you can, only by shifting the chemical potential down, you can make the areas on those curves equal. So, and this is what happens in graphene. This is a qualitative explanation. So the distribution for cold electron in graphene shown here by the blue line. There are two conductivity channels. There's intra-band conductivity in graphene, that's the conductivity of the states around the Fermi level, and inter-band conductivity like in normal semiconductors, band to band. And for the energies below the Fermi level, they are Pauli blocked. Yeah? That's why there's this dip. if by making electron gas and graphene hotter, we downshift the chemical potential, that means that we unblock some of the interband conduction channels here. So we add the spectral weight to the interband conductivity. Now we have to take it from somewhere else, and we can only take it from intraband conductivity. And this is the Terahertz conductivity. This is the illustration. This is not the exact solution. The frequency dependency of the conductivity on the frequency, on the energy, will depend on specifics of your graphene. So this is just the qualitative illustration of why graphene becomes resistive when you increase the temperature of its electron gas. Okay, but now we can add numerics. So if we just use two basic laws, the energy conservation, so we know how much extra energy we add to graphene because we know the absorbance, and then we add this absorbed Terahertz energy simply as heat. That will give us the new temperature for the hot electron distribution. And also at all times we want to keep the carrier density constant, and this will give us the temperature dependent Fermi level. We can perfectly well describe the measured conductivity of graphene simply by the static solution of the Boltzmann equation that I've shown you a few slides back. So this is basically hot electrons, low intraband conductivity. And this works very well in this very simple static-like approach until the fields of about 40-50 kilovolt per centimeter, which interestingly roughly coincides to the temperatures of up to 1000 Kelvin, which for our graphene was about the Fermi temperature. When you increase the field strength further, the static description will break down. It will not describe the data very, very well. So we decided to be very general and to build the model from the first principles by considering the dynamics of electron heat in graphene. So we know that you deposit the heat instantaneously. So graphene thermalizes, the electrons in graphene thermalize instantaneously when they receive new energy. But they cool down slow because cooling of electron in graphene occurs via phonon emission, and the dynamics is known. So the heating is instantaneous, few femtoseconds, cooling down slow, picoseconds. So now we put all this dynamics in a very simple model. We just propagate the Terahertz field through the model graphene. Then we can see the evolution of the electronic temperature as graphene interacts with the Terahertz field. So the gray area here is the absolute value of the Terahertz field, just to give you reference. And the lines here, they show the evolution of the temperature. You can see that graphene never cools down to the room temperature while the Terahertz field is in there. Yeah, that's because of this asymmetry between heating very fast and cooling slow. You always accumulate heat as you drive those fast currents, so it only cools down completely after the Terahertz field is long gone. And at least this model predicts that at transistor type fields of about 100 kilovolt per centimeter, the temperatures of electrons are about 7,000 to 8,000 Kelvin, which is very hot. All right, so this is the insights of our model. The input parameters is the measured experimental Terahertz waveform, and then the starting conditions for graphene, the Fermi level, and the momentum scattering time at the Fermi level, which you know from the linear characterization from Raman spectroscopy. Those are the only input parameters. Then you can propagate the experimental Terahertz pulse through graphene numerically, and you will get the numerically transmitted waveform. And now we can emulate the experiment, so we have the measured incident waveform and then numerically transmitted one, and then we can compare it to the real data, and this is how it looks like. So the symbols are the measurements, and the solid lines are the simulated experiment. And you see that the match is very, very nice. Again, this model has no free parameters. So on this slide, you see the entirety of our data at all frequencies from 0.4 to 1.2 terahertz, and also in the entire peak field range from 2 kilovolt per centimeter to 120 kilovolt per centimeter. All within one model, it fits perfectly. So no adjustment parameters. Now that the model works, we can apply it to the rest of our data. Many groups before us reported this subtle absorption of graphene, and the absorption, the Terahertz absorption, the frequency integrated absorption is the measure of intraband conductivity. So I think the first observation was by Dresden group, and then Kit Nelson and the rest. So again, so this is the data, and now we apply our very simple thermodynamic model to the data. So just heat balance, and this is how it looks like. So again, no fits, no nothing, just from first principles. It fits very, very nicely. Because this model gives us the instantaneous temperature, we can also integrate and see how much energy is actually deposited in the electron gas on time scale of interaction, because it's only the heat which is accumulated that reduces the conductivity of graphene, and we can see that for all peak fields that we use, it's about 15% of the Terahertz energy that is accumulated in the electron gas, and the rest ultimately goes to the phonons on time scale of interaction. And that brings me to the conclusions. So I hope I could convince you that the Terahertz conductivity of graphene is simply defined by the thermodynamic balance maintained within its electron gas and nothing else. And then the high electron temperatures lead to reduction of the chemical potential and therefore to reduction of intraband Terahertz conductivity of graphene. Thank you very much.